It's a really great pleasure for me to introduce Matthew Kwan, who is currently at IST Austria. Matthew has really many outstanding contributions in combinatorics, especially in random graphs. And today on our seminar, he will give a talk about his, as far as I understand, quite recent result on friendly bisections of random graphs. Please, Matthew.
Thank you very much. You know, it's a great pleasure to be speaking here today. Thanks for the invitation. Yeah, so I was just saying that so this is I guess I have 1.5 hours. I've got much less than that to say. I prepared for more than 50-minute seminar, so that means you should feel especially welcome to you know, interrupt me and ask questions and so forth. So feel free to either ask questions in the chat or just interrupt. Yeah, so I'll be speaking about a particular problem that we've resolved relating to bisections of random graphs. But I think, and well, I hope you'll agree that we've discovered, or at least developed some techniques that I think are of even more general interest. And so yeah, I hope, yeah. Anyway, so this is all it's based on a paper that's all joint work with Asaf Füredi from UC Irvine, Bhargav Narayanan from Rutgers, and Ashwin Mehtab Soni from MIT. Okay, so let me start with some motivation. So let me remind you about cuts in graphs, graph partitioning problems. So what a cut is just a partition of the vertex set into two parts, which for me I'll always be calling A and B. And then the size of the cut is just the number of crossing edges. So the number of edges which have one of their endpoints in A and the other of their endpoints in B. And then a maximum cut, or a max cut, is just a cut which has the maximum possible size. So I suppose there could be multiple max cuts, but that's a definition. And these are really standard definitions. This is a very important parameter and very important concepts in computer science. In particular, it's one of the most fundamental NP-complete problems to determine the max cut of a graph. But let me make another definition that's less standard, or at least this name is not so standard. But I'm going to define the friendliness of a vertex with respect to a cut to be the number of neighbors that vertex has in its own part minus the number of neighbors in the opposite part. So V is in part A, that's the degree into A minus the degree into B, and if V is in part B, it's the opposite. So maybe the reason you might call this friendliness is because maybe you've got like two tribes of people, the A tribe and the B tribe, and everyone in A is friends with the rest of A, and everyone in B is friends with the rest of B, and between them they're enemies. And so the friendliness of a vertex is the number of neighbors which are friends minus the number of neighbors which are enemies. Okay. Anyway, so a classical fact about the max cut, about any max cut, is that every vertex always has non-positive friendliness. There can never be a vertex with positive friendliness. And so the reason for that is that if you did have a vertex with positive friendliness, well, so that means I've got more neighbors in my own part than the opposite part. And that means that if I just switch that vertex from whatever part it's in to the other part, if I change the cut by just moving that one vertex, well, what would that do to the size of the cut? Well, the only edges that would sort of change whether they're crossing or not would be the edges incident to V. And if V has positive friendliness, that means I'm going to increase the size of the cut. And of course, if you've got a max cut, there can't be any way to increase the size of the cut, so this can't happen. Okay. Yeah. So of course this implies that every graph has a a cut in which every vertex is unfriendly, which I'll be calling an unfriendly cut. So every graph has an unfriendly cut. In particular, a max cut is an example. And obviously, if you want to find, if you want to algorithmically find an unfriendly cut, that's really easy, and you can do it efficiently. You just repeatedly check whether there is a vertex. So you start with some arbitrary cut, check whether there is a vertex which is friendly, and if there is, you swap it, and you just keep going until you run out of friendly vertices. And of course, this has to terminate eventually, because each time you do this operation, you're increasing the size of the cut, and there's a maximum it can reach. Yeah. So it's important, by the way, that if you have a friendly vertex and you move it to the other side, that's not necessarily decreasing the number of friendly vertices. So if you look at how the number of friendly vertices changes, it could behave in some weird way. The only thing you're controlling here is the size of the cut. Okay, so it is a basic fact that every graph has an unfriendly cut, it won't be super relevant for this talk, but I thought I would mention that curiously, this is actually false for infinite graphs. So the fact that moving a friendly vertex increases the size of the cut, of course, this doesn't show anything for infinite graphs. And so Shalat and Milner made this quite famous discovery that for uncountably infinite graphs, this is just false in general. And I think it's an open problem whether it's true for countably infinite graphs. It's called the friendly graph conjecture. Yeah. So I should also say that I don't want to say too much about motivation and applications and so forth, because it's not really the point of this work. But as I said, the max cut parameter is something important in computer science, and the problem of finding an unfriendly cut is like a local version of the max cut problem, which for various theoretical reasons is apparently interesting, and apparently also in statistical physics. Also, the max cut could be interpreted as the Hamiltonian the maximum Hamiltonian of some spin glass system, and for some reason, local optima are interesting in that setting as well. Anyway, this is all about the max cut and unfriendly partitions. There are a few other fundamental types of graph partitioning problems. Perhaps the most obvious one you might want to ask about is the Mincut problem, where you ask the opposite question. I would like to find a cut with minimum possible size. And obviously, for this to be an interesting question, I need to restrict my attention to non-trivial cuts, where I impose that both of the parts must be non-empty. Otherwise, you can find a cut with size 0. Now, in many ways, Mincut is a much simpler and less interesting problem than max cut, because, for example, like very often, the best thing you can do, for example, in a random graph, the best thing you can do is just put a single vertex on one side and the rest of the vertices on the other side, and that will be the minimum cut. And in general, you have this thing called the Mincut max flow theorem, which gives you a polynomial time algorithm to compute the Mincut. But one way in which the Mincut is not simpler than the max cut is that you do not have a similar type of local property. It is not in general true that the minimum cut is friendly. It's not true that every vertex has non-negative friendliness. And the reason for that is just basically because I've defined this in such a way that I'm not allowing degenerate partitions. So you can still do a similar kind of sort of iterative thing where you try and, if there's an unfriendly vertex, then you move it. But you're not allowed to, I mean, if I was in a situation where I had one part consisting of almost all the vertices and the other part consisted of a single vertex, which is obviously very unfriendly. I mean, if you've got a single vertex in a part, then all its neighbors are on the other side. You're not allowed to just move that single vertex to the other side to make the cut smaller. That would give you a degenerate cut. And actually, to say, I mean, apart from the fact that the Mincut need not be friendly, there exist graphs for which there is no cut at all, in which every vertex is friendly. So, for example, a clique or a star both fail to have this property. So in some ways, the property of having a friendly cut, or the problem of finding a friendly cut, is more interesting than the property of having an unfriendly cut. And actually, it's an NP-complete problem to decide whether a graph has a friendly cut. But there are a few nice theorems in this area. Perhaps the most famous one is a theorem of Stibitz, which answered a question of Carsten Thomason. So he proved that there is always a cut which is sort of almost friendly, in the sense that each vertex has friendliness at least -1. Yeah, so each vertex has at most one more neighbor on the opposite side than its own side. So actually, Stibitz proved something a little bit stronger, well, substantially stronger than this, but we won't worry about that for now. Anyway, so this theorem is saying that you can always find in any graph an almost friendly cut in this sense. And there is also this, I think, quite beautiful conjecture of Bahn and Lineal, which sort of puts the almost in the other place. That says you can almost always find a genuinely friendly cut, in which every vertex has actually as many neighbors in its own part as in the opposite part. So they conjecture this in the sense that for every D, there are only finitely many D regular graphs which do not have a friendly cut.
Sorry, is everything known for random D regular graph? Is it true that it has such a cut, or? Yeah, so we this is coming up right now. So yeah, so that's a very strong sense of almost all, stronger than you usually see in graph theory. The fact there's only finitely many exceptions. But you can also ask about random graphs. So yeah, it's a theorem of Lineal and Lewis that if D is even, and I actually learned while giving this talk when Nati was in the audience that it's they only did the even case. The odd case is still open. But at least if D is even, then asymptotically almost every D regular graph on n vertices has a friendly cut. And you can also ask, I mean, you don't necessarily need to restrict yourself to sparse random graphs, to random regular graphs. You could also ask this about GNP, GN1/2 or something. And we'll get to that in a second. Okay, but so I suppose the moral of all of this stuff is that, well, so friendly cuts are harder to think about than unfriendly cuts. It's not true that they just sort of always necessarily must exist, but in several different ways, we have sort of almost results, and so we sort of know mostly what's going on. Now, in contrast to that, well, okay, so we've talked about max cut and min cut. Now let's talk about max bisection and min bisection, which I think so max cut, max bisection, and min bisection is sort of the four most important graph partitioning problems. So what a bisection is it's just a cut where the two parts have equal size. So of course that is only possible when the graph has an even number of vertices. So I suppose when it has an odd number of vertices, I could demand that the two parts differ by at most one, but let's perhaps not worry about that for now. But then so obviously the min or max bisection problem is trying to minimize or maximize the number of crossing edges in a bisection. And these are both NP complete problems. And actually they are equivalent problems. So a min bisection of a graph is the same thing as a max bisection of its complement. And perhaps the easiest way to see this is by considering these friendliness random variables, well, these friendliness variables that we've defined. You need to observe that maximizing the size of a cut or maximizing the size of a bisection is the same as maximizing the sum of friendlinesses over all the vertices. That's just you can check that's just like a linear transformation of the objective function. If you have a bisection, then you have the property that if you take the complement graph, that's basically just the same as flipping the signs of all the friendlinesses. So maximizing and minimizing are the same after taking complements. Okay. Now, just like for
the max cut and the min cut, you can ask for local optimality properties. So maybe I want to ask for a friendly bisection or an unfriendly bisection. Now, it turns out, for reasons that I will explain shortly, that bisections are much more difficult to understand than general cuts. And very little is known. But perhaps the most well-known thing here is a conjecture due to Füredi. So he conjectured that almost every graph has a bisection in which almost all vertices are unfriendly. So this is putting the almost in several places. So that's the informal statement, but the formal statement is this. So what Füredi really conjectured is that if you take a random graph Gn1/2, so what that means is that I take a set of n vertices. Vertices are not random. I have a fixed set of n vertices, and for each pair of vertices, that pair could be an edge or it could be not an edge, and I flip a coin to decide whether to put an edge there.
I'm sorry.
Equivalently, it's
do you know that in a random graph there is a bisection in which almost all vertices are friendly, not unfriendly, but friendly? Or
yes. So I've just described that. So the max bisection and min bisection are equivalent problems. The version of this problem with unfriendly and friendly are less obviously equivalent, but still equivalent. So if you take the complement of Gn1/2, then that's yeah. So the complement of Gn1/2 is still Gn1/2, and you might think that just flips all the friendlinesses, and it basically does, but there's a tiny off by 1 error because a vertex can't be adjacent to itself. This off by 1 error doesn't really do anything, but yeah. So actually, Füredi conjectured the friendly version. I've written the unfriendly version here because I don't have to worry about this off by 1 thing as much. But it's not really something I want to talk about too much. But anyway, to finish describing the conjecture, so he conjectured that in Gn1/2, with high probability, meaning with probability going to 1 as n goes to infinity, I can find some bisection such that all but a vanishingly small proportion of vertices have non-positive friendliness. Almost every vertex is unfriendly. And here's that remark that I just made, that friendly and unfriendly are basically equivalent up to some off by 1 issue that doesn't really matter.
Sorry, and is it clear that we cannot remove this little of n condition or not?
That's a very good question. So at the end of my talk, I have some open problems. So to sort of spoil that, so there's a good reason why you would make this conjecture with the almost in both places, which I'm about to describe. But I think it's quite likely that the same statement is true without this little O of n. That in fact, every vertex has every vertex is unfriendly. Our proof isn't going to do that, but I think it is true. Yeah, and in fact, you could make it. In fact, there's sensible things you can ask about, not even for GNP, but for all graphs. So it's not true that every graph has a bisection in which every vertex is friendly. But something close to it may be true, and there's a conjecture by Bolovash and Scott along these lines, which I'll tell you about at the end. But anyway, for now, this is our question. In a random graph, I want to find bisection into 2 parts of equal size, such that almost every vertex is unfriendly. Okay, so why is this a sensible thing to ask? Well, I don't know exactly why Füredi decided to ask this, but here is my guess. A reason you might believe this is that it sort of makes sense in expectation, assuming everything is independent. So what is the number of bisections that I have to choose between? Well, it's n choose n over 2, which is about 2 to the n, up to some. It's like 2 to the n of the square root is the asymptotics of that. If I fix you a bisection and I ask what is the probability that this particular bisection is unfriendly in my random graph, well, that's actually a highly non-trivial thing to compute. But if I make an independence assumption, if I look at a particular vertex, what's the probability that vertex is unfriendly? Well, I've got some number of neighbors in my own part. I've got some number of neighbors in the opposite part. Those are both binomial random variables. They're independent. They have basically the same distribution. Again, there's an off by one issue because I can't be adjacent to myself. Okay, so the difference of two things that are almost the same, it has about a half chance of being positive and about a half chance of being negative. So if each vertex is unfriendly with probability about a half, if I naively assumed that each vertex were independent, that would say that the bisection is unfriendly with probability about 2 to the minus n. And so now it's a little bit ambiguous whether, I mean, you've got 2 to the n bisections and the probability is 2 to the minus n. If you multiply those numbers by each other, well, it's too close to 1 for maybe for you to make a conclusive guess. But if I only ask for almost all vertices to be unfriendly, if I allow like an epsilon fraction of them to be to not be unfriendly, well then suddenly the product of these two things becomes exponentially large. So I expect there to be exponentially many bisections which do the job. Now, yeah. So I should really stress that is what I just said is really just a heuristic because it is not true that the vertices are independent, but the correlations here seem to work in your favor. So if I know that a vertex is unfriendly, that sort of correlates with the global event that there are many crossing edges, like the size of the cut is large. And so if I ask about two different vertices, they're both unfriendly, they both correlate with the same global event that the cut is large. So you know, if they're positively correlated, this should be a conservative heuristic. Yeah. In fact, I think this is true with room to spare, and this is perhaps a reason to believe why this should be true with no little o. In fact, every vertex should be possible to find a bisection where every vertex is friendly. Okay. Any other questions? Okay, so that's Füredi's conjecture, and we proved it. So together with my co-authors Asaf, Bhargav, Ashwin, and Mehtab. And so we didn't just prove that an unfriendly bisection exists, but we actually have a way to find it. So we have an efficient randomized algorithm that actually finds an unfriendly bisection in a random graph. Okay, so I suppose I will spend the rest of my time telling you how to prove this. Okay, so yeah, there's really a lot of different ideas that I think are interesting for different reasons, but here is the starting point. Yeah, so remember on the first slide, we proved that if you have a max cut, then you can't have a friendly vertex because you can make a local change if you did, and you make a local improvement. Now, for bisections, we're not allowed to make this local change. We're not allowed to just move a vertex to the other side because that would break the property of being a bisection. But of course, we can just swap a pair of vertices. If I have a friendly vertex on each side, if they both have positive friendliness, I can swap them, and doing that will strictly increase the size of the bisection. Now, yeah, it's a bit less obvious because you have to worry about the edge between those two vertices, but if you check it, you'll see that this is true. Okay, so this tells you something. So this tells you as a corollary that there is a bisection, in particular a maximum bisection. At least half of the vertices are unfriendly. So either all the vertices in A are unfriendly or all the vertices in B are unfriendly, because otherwise there would be a friendly vertex in both parts and you could swap them. So if you would like to find an unfriendly bisection, something it might make sense to try is to start with an arbitrary bisection and just repeatedly swap pairs of friendly vertices as long as you can. But obviously the problem is that, you know, it is possible that you somehow have to rule out the possibility that when you get stuck, so when there's no longer a friendly vertex on each side, it could be the case that things are super imbalanced and one side is 100% friendly and the other side is 100% unfriendly. And then you're nowhere near proving the theorem, but you're stuck. So if you want to overcome this, you might try to come up with, some kind of, I mean, this is a very dumb kind of swapping rule. You just greatly make choices. Maybe you come up with some sort of crazy better swapping rule that tries to like simultaneously increase the size of the cut and also at the same time, keep the number of friendly vertices balanced in some way. So that sounds like a thing you should try. And as far as we can tell, none of that seems to work, or at least we weren't able to do anything like that. But one very simple thing that we might try is to sort of use the probabilistic method. So to start from a random bisection and repeatedly swap random friendly vertices. So the idea here is that, maybe in principle it's possible that if you do the swaps in some bad order, you might end up with some really imbalanced situation where one side is really friendly, one side is really unfriendly, and you get stuck. But you sort of have to concoct things that look like that. And you might say that probably typically, if you make typical choices, that's not going to happen. Especially because you're in a random graph and everything is nice and symmetric. You should hope that maybe this is unlikely to happen. Yeah. So I should say, by the way, that of course, this is something that as soon as you come up with this idea, you can just immediately try it on a computer. And so we did that, and it does seem to work. And so if all you cared about was actually finding an unfriendly bisection without proving that it works in general, that this is immediately something you can do. So the key observation so this, despite the fact that on a computer this seemed to be true, it does seem a little bit scary to try and actually study what's happening when you do these random swaps. But the key observation that sort of gave us a bit of hope here is that actually you don't really need to understand what's happening in this kind of random swapping process. You don't need to actually track what's happening to the degrees and the number of friendly vertices and so on. The only thing you need to understand is that the situation is concentrated. So to elaborate on that, so let me define xt to be the number of unfriendly vertices in A in the first part after t swaps. So if I could show that xt was concentrated, so if I could show that with high probability it was close to its expected value, and I would get that from, say, Chebyshev's inequality by showing that the variance is little o of n squared. Well, that would imply that by symmetry, whatever this expected value is for part A, I have exactly the same expected value for part B. So here I'm crucially using the symmetry of the random graph. So whatever the number of friendly vertices is in part A, I've got the same amount in part B with high probability, because both of them will be concentrated around the same expectation. And of course, that's exactly what we need, because the only thing that's preventing us from using this naive idea is the fact that things can get imbalanced. The number of friendly vertices could start to differ in the two parts. So this is this is a very helpful observation, that the only thing I need to do is show that statistics of the process concentrate without actually showing what they concentrate around. And that'll allow me to do this.
Am I right that this really just immediately implies what you need, this observation?
Yeah. So if you could have a probability small enough to take the union bound over all steps, it would literally immediately imply. The way they're written here doesn't quite as obviously immediately imply it, but I guess I'm just trying to convey the idea that concentration as a general thing is something that would be very helpful here. Yeah. Okay. Yeah. So this symmetry argument is actually very subtle and sort of very sneaky, because as we'll soon see, if you actually want to study the evolution of this process, it's a very, very delicate analysis. And the fact that you only need concentration is quite important. Okay, so we need to show that something concentrates. I suppose what we should do is start to think about what are the general tools that we have to understand concentration of random graphs and random graph processes, and let's see if we can apply them here. So in case you're not familiar, let me tell you that perhaps the most general purpose thing that you can try if you want to show concentration of some kind of a complicated combinatorial process is something called the efferentstyle inequality, which is a kind of perturbative inequality where you're trying to show that your random variable is not sensitive to fluctuations in some underlying probability space. So the setting here is that I have a function of n independent random variables, x1 through xn, and that's the random variable I want to understand. So for example, if I have a function of a random graph, I would put a random variable for each possible edge. So there's a coin flip for each edge, and my random variable is somehow a function of these coin flips. And so if I want to show that this random variable is concentrated, if I want to show that it has small variance, all I need to do is to sort of give an upper bound on the effect of resampling, randomly resampling one of my underlying random variables. So to be precise, I consider the expected square of this quantity. So yeah, the expected change when I randomly resample the ith random variable. Okay, and then you sum this up overall I, and that's an upper bound of the variance. So this is very useful in a number of settings because it does exactly what we were sort of after, and it gives you some sort of concentration without actually telling you what it's concentrated around. You just need to show that small changes in the underlying random variables do not have a big effect on the outcome. So for example, if you want to prove that the chromatic number of a random graph is concentrated, this will do it for you. So often people will use something called the Azimuth-Höfting inequality. This is a more robust, doesn't give us good tail bounds, but it's more robust in terms of when it applies. Or for example, if you want to study the shortest traveling salesman path in a random set of points, there again, it's hard to understand what is the expected shortest path, but this will show you that it's concentrated. This is a great general tool for all sorts of things of this nature. Yeah, so in our setting, we have a function of a random graph. So it's a function of a random graph and also a function of the random choices we made during the process. But if we just consider the edges of the random graph, somehow we want to show that if I just change one edge of my random graph, that's not going to have much of an effect on the behavior of the process. So if I could show that, then I would be in good shape. As far as I know, this is true. So it seems very plausible to me that the process is robust in this way, that changing a single edge is unlikely to have much of an impact. But I don't know how to prove this, and it just seems that proving this is about as hard as proving the thing that I wanted to prove in the first place. Because, yeah, I mean, what you need to rule out here is some kind of contagion where, so like I'm flipping a random friendly vertex, so the process will change a lot if somehow making some small change to the underlying graph caused a lot of vertices to like just pass the threshold from friendly to unfriendly. Like if there were a lot of ties and the edge sort of broke a lot of ties, then this would be bad. But this can happen like deep into the process. You could have some seemingly small thing that sort of has some big contagion effect on the whole process. And it just, so I can't rule out the possibility that some very sneaky, cheap argument of this type will work, but we couldn't do it. Okay, so that's a shame because this is kind of the softest thing you might try to do. Okay, but that's maybe okay because there are lots of other standard things you can do to try and study random combinatorial processes. And perhaps the next most well-known thing is something called the differential equations method, which has seen some enormous success in studying all sorts of random graph processes and random combinatorial processes. Yeah. So I thought I would sketch the general idea in case you're not, for those of you who are not probabilistic combinatorics people. So yeah, so the way this works is that I have my favorite random process and I want to somehow design or define an ensemble of random variables that evolve with the process that somehow track the evolution of the process, somehow summarize the evolution of the process. And the critical thing that I want this ensemble to satisfy is that the expected change in each of my random variables, so the expected change at a single step, can be approximated in terms of the other variables in my ensemble. Yeah, so like a common example of this would be something like an H-free process or an H-removal process, where maybe at each step I choose a random triangle in my graph and I delete it or something. And so then you might say, let me track like the degrees in the graph that I've got at each point. So I've got, an ensemble of random variables, each measuring a degree, and I want to make sure that the change in a degree is somehow approximable by the other degrees or something. So when you've got this, you've got something that vaguely resembles a system of differential equations. So if the change in the current value, if the stepwise change can be approximated in terms of the current values, that's like a system of differential equations. And so you can solve the system of differential equations to make like a guess, to get an ansatz for the trajectory of the process, you know, by integrating these differential equations. And then you just need to show that the process is likely to actually follow the trajectory that you've just computed. And usually that's pretty easy with some martingale concentration inequality. Basically, so you subtract the process from the like estimated trajectory, and the computations you've just done to solve these differential equations will basically tell you that this is essentially a martingale and it's concentrated and everything works. Okay, so that is what the differential equations method is. It's definitely not as soft as an approach. So usually you have to do a lot of calculation to make this work. You have to actually solve some differential equations. But actually, because in our case, all we want is concentration, maybe we don't even need to solve some differential equations. Maybe we just need the fact that there is a solution or something. Anyway, so that's a thing. But unfortunately, so this is a good starting point. So this is related to what we will end up actually doing. But this is not the differential equations method is not the right thing for this particular random process. So maybe, so the question is, what random variables should I track for my process? Remember, my process is that I've got a bisection and I'm picking random friendly vertices and swapping them. Like, what should I track? So maybe the first thing you would guess is that I would have a random variable for each vertex measuring how friendly that vertex is. But that's just the wrong kind of thing for the differential equations method, because the whole point about the differential equations method is that I'm showing things are concentrated around some trajectory. But all the friendlinesses are just concentrated around zero. Like the number of neighbors in my own part minus the other part, with high probability is going to be close to zero. And the whole point of this process is that, so there's some fluctuation around zero, and sort of what's happening in that window of concentration, like what's the fluctuations that are happening there, that is what is driving my process. So sort of concentration around something is not the right thing here. Yeah, like you need to understand what's happening within the window of concentration. So it doesn't just work to track the friendlinesses of each of my vertices, but maybe what I should be doing is tracking some kind of aggregate statistic. So maybe I want to track like the number of friendly vertices in each part. And this is kind of a good idea, but unfortunately, a single statistic like the number of friendly vertices in each part is just way too little information to actually predict what is going to happen at the next step. Like, somehow you really need to understand the whole distribution of what all the friendlinesses are in order to predict sort of the distribution at the next step. And it's hard to summarize, well, it's hard to imagine how you would summarize sort of this kind of distributional information in a differential equation. Okay, so this doesn't work, but as I said, this is getting a little bit closer to something that does work. Okay, so let me start telling you about some of the ideas that we did actually use in this proof. So the first thing is that life becomes much simpler if you do something called nibbling the process. So what I mean by that is that so the random process that I've defined so far is where each swap, so you're iteratively making these random swaps. Each swap depends on the entire history of the process. So there's like at least n, like maybe n squared steps of the process, and each step depends on all the previous steps. But instead of doing lots of little swaps, I can instead do a small number of big swaps, where at each big swap, I swap a large number of vertices all at once. So the reason I call this nibbling is because it's related to the Rödel nibble and probabilistic combinatorics, which is some kind of greedy packing thing, where instead of somehow you want to like randomly greedily pack things one at a time, but it's very helpful to pack things in bites, to like nibble, to do things in chunks. So number one, why does that help? And number two, why can you even do this? So the reason you can do this is that, is this lemma here. So this lemma says that in every bisection in a random graph, there are not too many vertices with friendliness extremely close to 0. So almost all vertices have the absolute value of their friendliness being about the square root of n. And the reason for this is just a union bound. So there are only at most 2 to the n bisections, meaning that anything that happens with sort of super exponentially small probability just doesn't happen for any bisection. And now for each vertex, the friendliness, it's as we said, it's a difference of 2 binomial distributions. So by the central limit theorem, it's approximately Gaussian. And the standard deviation is square root n. So the probability that you see a deviation that's like 0.01 times the standard deviation is just very, very small. And so the probability that you see this for, n different vertices or epsilon n different vertices is super exponential. Well, is smaller than 2 to the minus n. And so I can just take the union bound to see that, almost every vertex has friendliness of order square root n. Okay, so why is that relevant for nibbling? Well, what it means is that if I swap a lot of friendly vertices at once, so if I take a chunk of epsilon n vertices on one side and epsilon n vertices on the other side and I swap them all at once, it can't be the case that all of them have friendliness close to 0. So this chunk, like swapping these chunks must have had a big impact. Like almost all the things I swapped had friendliness of order square root n. So I've changed the size of the cut by n times square root n. I've made some enormous effect on the size of the cut. And n times the square root of n is the magic number here, because you can also prove using a union bound that in a random graph with high probability, every bisection has size falling in a window of size n times square root n. And so, so this is just a union bound plus the Chernoff bound, you get this. So if each of your big swaps changes the size of the cut by something of order n to the n times square root n, and if the size of every cut lies in a window of size some constant times n times square root of n, that means this process can only go for a constant number of steps. And so the scaling here is about e to the 1 over epsilon steps if I'm swapping epsilon n vertices at a time. So what that means now is that if I want to prove that there is an almost friendly bisection, so if I want to prove there is a 99% unfriendly bisection, there's some constant, maybe 1,000,000. I just need to study this process for 1,000,000 steps. At some point, it can't be the case that for each of these steps that I still have many friendly vertices, because at each step I'm increasing the size of the cut by too much. Okay, so we still have this sort of highly dependent process, but now I only need to study for a constant number of steps, and that's very good, because now I don't need to union bound over many steps. I can just individually prove something for each of a constant number of steps. Okay, so that's the first idea. Okay, I see I've successfully gone more slowly than, so we could actually take a break. Okay, so where we were at, so we were studying this process where we want to show that there is a unfriendly bisection, a bisection where almost all vertices have more neighbors on the other side than their own. We were trying to study this nibbled process where at each step we check if there's many friendly vertices on both sides. If there are, we take a big chunk of them and swap them all at once. And so we've seen that this process must terminate after a constant number of steps. And so we would like to show that this process is in some sense well concentrated at each of those steps. Okay. Okay, so that was, this nibbling idea was the first idea. Here is a second important idea, which is maybe the most important idea, which is that, so the whole problem is we're trying to prove that something is concentrated. So we want randomness to show that things are concentrated. And so at the start, we have a random graph, but then at the subsequent steps, all we have is the randomness of the swap. So, we have a random graph, we look at it, we divide it into two parts, and then at each step, we swap random friendly vertices. And that randomness at the start of the random graph is very valuable. And instead of exposing it all at the beginning, I would like to sort of save the randomness for the duration of the process. So what I mean by that is that instead of exposing the entire graph at the beginning, I just expose some partial information at each step of the process. So at each step, we don't just have the randomness of the random swap, we also have some residual randomness from the random graph itself. That's very, very helpful. So to be a bit more specific, so the way that our process works is that at each step, I want to swap some friendly vertices. I want to take some friendly vertices on both sides and swap them. And in order to know how friendly a vertex is, I need to know the degree into A and the degree into B of each vertex. So then I subtract those from each other, and that'll tell me how friendly I am. But the point is that that's all I need to know. And so I only want to reveal that information and nothing else. So meaning for each vertex, I reveal the size of its neighborhood in A and the size of its neighborhood in B, but I don't tell you what the neighbors actually are. So they're still random. Yeah. So after having revealed this information, my random graph now has some conditional probability distribution. All I've exposed is some degrees. Namely, I have a random graph with degree constraints. Now, this is a very unusual thing to do. So iterative exposure is not a new idea, but usually you would use the fact that the edges are independent, and maybe at each step you would expose some subset of the edges or something. And then, you know, having exposed only some subset of the edges, the rest is still independent. That doesn't work for us. We sort of need to know degrees. So our conditioned object is rather strange, a random graph with constrained degrees. And sort of naively, if you sort of didn't know anything about the theory of random graphs, you might think this is a totally impossible situation, because an Erdős-Rényi random graph where you flip a coin for each edge is like obviously a thing that you can understand. But if I'm conditioning on degree information, suddenly I lose all sorts of independence. But it turns out that random graphs with constrained degrees behave in basically the same way as ordinary Erdős-Rényi random graphs, at least with respect to sort of large-scale properties like concentration and like degrees and subgraphs and things like this. It's just way harder to prove stuff. But we didn't have to invent this stuff, so the theory here has already been developed. There were some initial ideas by McKay and Wormold, and we also need a bipartite version due to Canfield, Greenhill, and McKay. But just to say a little bit about how you study constrained degree random graphs. This is a uniform distribution. So if I condition on the degree information, I'm now taking a uniformly random graph given that I've got certain degrees. So that's just sampling from the set of all graphs with those degrees. So it's really a counting problem. If I want to prove things about constrained degree random graphs, I need to count random graphs with a given degree sequence. And the way you do this is by defining generating functions in a very large number of variables. So the number of variables is the number of vertices. And then you do some very high dimensional complex contour integral to understand the coefficients of this generating function. So I would not a priori have maybe guessed that this works, because usually you don't have the dimension being quite so high as this. But this does work, and you can use this stuff to sort of get your hands on constrained degree random graphs. So yeah, so to summarize, so at each step, we only expose the relevant degree information that we need to know what the friendliness of every vertex is. Meaning that at each subsequent step, we basically still have a fresh random graph that we can use to establish concentration at the next step. Although, of course, it's a constrained degree random graph. It's a bit harder to work with than an ordinary Erdős-Rényi random graph. But still, we can do it. Okay. And remember, we only need to do this for a constant number of steps. Okay, so at each step, we basically have a fresh random graph to play with. So now we just need to decide what we are going to sort of track as the process runs. And basically, the only way that we were able to make this work is by keeping track of the entire distribution of degrees at each step. So keeping track of really all the information that you've exposed so far as a distribution. So let me be a little bit more precise about that. So for each vertex, I record like a log, which records the history of where that vertex has been during the process. So there's a constant number of steps, and at each of those steps, the vertex was on one of the two sides. So after k steps, there's 2 to the k possible logs. Like I was in part A, then I was in part B, then I stayed in part B, then I went back to part A, and so forth. So 2 to the k is a constant, so I can partition the vertices according to their logs, and I have pretty big parts of vertices. And then, yeah, and so then for each part, I want to record the entire empirical distribution of degrees from that part into the other parts, or from that part into all of the parts, including its own. So namely, I look at all the vertices in one of my parts, which I'll call Vx, and each vertex in Vx has a vector of degrees into the different parts. I look at the multiset of all those vectors, and I look at the uniform distribution on that multiset. This is the empirical degree distribution. So at step k, I have 2 to the k different, 2 to the k dimensional probability distributions. And somehow these are summarizing all the relevant information about the process. And so then I want to show that this entire empirical degree distribution concentrates in some sense around some ideal distribution. Yeah. So it's going to be something like a multivariable Gaussian distribution. And so what it means for an empirical distribution to concentrate around an ideal distribution is that with high probability, the distance between the distribution you have and the ideal distribution is small, according to some metric on distributions. Yeah. So to maybe, this is a little bit abstract. So to give you an example of this, so at step 1, before I've done any swaps, I just have 2 parts, A and B, and there are 2 possible logs. I'm either in A or I'm in B. And so I have 2 different 2-dimensional probability distributions, and both of those is going to be a bivariate Gaussian distribution. And that's just because the degree into A and the degree into B are both binomial by the central limit theorem. They're basically Gaussian. So that's what happens in step 1. On step 2, I'm going to have a 4-dimensional probability distribution because I could have been in part A, then part A, or part B, then part B, or part A, then part B, or part B, then part A. And the distribution you're going to get, so you're going to get 4 distributions. Each of them is going to look approximately Gaussian, but it's going to be twisted in some way because you're working with degree constrained random graphs. And so it's not going to quite be Gaussian. It's going to be Gaussian-like in some sense. And the 2 to the k step, you've got 2 to the k different 2 to the k dimensional probability distributions. Yeah. So you really do need to know the entire empirical degree distribution. You need to know approximately what is the entire empirical degree distribution if you want to be able to understand the distribution at the next step. Distribution is a very complicated aggregate of the distribution at previous steps. Okay. So now we know what to track. We're tracking the empirical degree distributions, and we have a way to, in principle, track it. So we have this machinery of McKay and Wormald and Canfield, Greenhill, and McKay, which gives us a way to count graphs with given degree sequences, which gives us a way to compute things about constrained degree random graphs. So in principle, we could use this machinery to give some formulas, to give some very, very complicated combinatorial sum that expresses the typical empirical degree distribution at step k. But working with these direct expressions directly is a huge disaster, because I mean these formulas already, they're complicated formulas, and you're summing them. It's like it's a very deep iterated sum of the things you need to count and average over and so forth. I don't think there's even much chance of things having a closed form expression. So actually tracking what's happening during this process seems almost prohibitively difficult. But luckily we remember that we don't actually need to track the process. We just need to show that it concentrates. And so that's basically what we do. So unfortunately it's not true in the generality that if I know that I concentrate around something at step k, it's not possible to deduce in a black box way that I concentrate around something at step k+1. But if you maintain a little bit more information, this sort of thing is true. So on this slide, I've written what exactly you need to maintain inductively through the process. So the first condition here is just some technical thing, because in order to use these techniques of McKay and Wormald, I need to consider large graphs. So I need my partition to be far from being degenerate. So each of my 2 to the k parts need to be quite large. And the second condition is the important thing. So I need to show that there is some ideal distribution. Well, there are some 2 to the k ideal distributions, Lx superscript k, having the property that the empirical degree distributions concentrate around this ideal distribution. Meaning that with high probability, according to, and what we use is something called the Combgeo distance. According to the Combgeo distance, our empirical distributions are close to these ideal distributions. But in order to make this actually work, I need some sort of regularity from my distributions. The first thing here is that I need my distribution to not be too spiky. Like it would be bad if there was a single point which had large probability that would sort of throw off the estimates. For reasons because, so the Combgeo metric is a thing about, it's about like breaking up 2 to the k dimensional space into lots of little boxes and sort of comparing the probability mass in each of the boxes. The boundaries of the boxes cause issues, and so I can't allow things to be spiky. Like I can't allow the boundary to contribute very much. So you need an anti-concentration condition, and you also need sort of the tails of your distribution to not be too fat. So you want there to be a sort of a small region which contains almost all the probability mass, and the property that we need is called sub-Gaussianity. It's in some sense dominated by a Gaussian distribution. Yeah. So if you have this entire list of properties at step k, then it is possible to inductively maintain them to step k plus 1. Yeah. And so this is all by considering a partition into boxes and sort of refining the partition at each step. In fact, coarsening the partition. So it's quite fortunate that you only need to do this a constant number of times, because you study this process for a constant number of steps. Because the error terms are really enormous at each step. Like whatever the error terms are, it's like you're taking the square root of the error terms at each step, just because you have to coarsen this entire partition at each step. And so it will only be possible to continue this for like log n steps. So that's luckily constant is all we need. Okay, and so that's basically the proof. Yeah, so to summarize, we had this iterated swapping process. We nibbled the process, so at each step we were making a big change, which means we only needed to study the process for a constant number of steps. And we exposed the information iteratively, so we only exposed the information we actually needed for each step, meaning we still had residual information about the random graph at each step with which we could establish concentration. And then the stuff that we actually tracked was all this. Okay, yeah, and I think this is really quite an unusual way to study a random combinatorial process. At least we don't know anything else quite like this. Okay, so let me finish with some further directions that I think would be interesting. So the first thing is that this is a pretty technical paper. We worked quite hard to establish the concentration, but sort of the reduction to the problem of establishing concentration was really very simple. And so this proof would get a lot softer if we had some way to show concentration without getting our hands quite so dirty. So some way to make efferentstyle work, or to maybe invent some new kind of concentration inequality that only uses the kind of information that we actually have. Because there is certain types of like symmetry information and so forth that we do have access to. But yeah. So that would be interesting. The second thing is exactly what was asked earlier. I've proved that you can find a bisection where almost all the vertices are unfriendly, but maybe I want a bisection where all the vertices are friendly. So the moment heuristic suggests that this should be true. And also one of my co-authors, Mehtab Soni, did some compare experiments. And the swapping algorithm on its own, where you just swap pairs of friendly vertices, does not seem to take you all the way. But if you introduce a bit of random noise, like if you add some random swaps to sort of break out of local optima, then it seems that you do typically find a completely friendly bisection. And I think it would be very interesting to prove that. Yeah, our methods, I think, are really not suitable for that, because we can only do things for a constant number of steps, and at each step there's you need like epsilon n unfriendly vertices to play with. Yeah, so that's one thing. And the third thing is it actually makes sense to ask these questions not just about random graphs, but about arbitrary graphs. And so Bolobash and Scott conjectured that in any graph at all, you can find a bisection where every vertex has friendliness at most one. So this would be like an analog of Stiglitz's theorem for friendly cuts. That I can find a bisection where every vertex has at most one more neighbor in the other part as my own part. So this is probably really hard, but I'd personally be interested, even if you could prove this for any, like even for a quite restricted class of graphs, like if you could prove this for quasi-random graphs, I think that would be interesting, because I mean, often when you prove things about random graphs, all you really needed was some sort of pseudo-randomness condition. But here, because we're iteratively exposing things and using this constrained degree random graph stuff, we really essentially needed an actual random graph. And I don't know how to do things for any reasonably big class of non-random graphs. That potentially it could even be that the random process we considered works for quasi-random graphs, but I don't know how to prove it. And finally, I think that the ideas in our proof are of more general interest, and it would be nice if there was more applications. So already, two of my co-authors, Ashwin and Mehtab, have discovered that these types of ideas can be used in a completely different area to study something called majority dynamics in random graphs, which is some kind of dynamic system where you've got a bunch of voters and they're either on team A or team B, and you change your mind according to what most of your neighbors think. Yeah, so Ashwin and Mehtab managed to solve some conjectures in this area using exactly these types of ideas. Okay, so that's all I had to talk about. That's the end of my talk.
Thank you very much. Maybe I start with questions. Can you switch to the previous slide?
Mm-hmm.
So as far as I understand you, so the first thing is just how you define the process of how you swap these blocks, how you define these blocks and how you swap them. But I have no idea how you prove all the remaining. So do you use this machinery that was developed by Mikey and others for all of them, or yeah? So
even for the first one, actually. So for example, at the second step, I've got 4 classes. For example, the vertices that were in part A at the first step and were in part B in the second step. And so why should that be large? I mean, you need to prove something. So yeah, so it's certainly true that, yeah.
So you choose the blocks that is the best one, right? Not just or out of
yeah, but so it could be the one that's the best at step 1 is disjoint from the one that's the best at step 2, and that would be bad because I want all the intersections to be large. So actually, none of this is trivial at all. Yeah, so so this is all computations in a constrained degree random graph model. You have to do all sorts of computations but at the first step, when I have a genuine random graph and I don't have to worry about this constrained degree stuff, it's largely a second moment method. So if I want to show that an empirical distribution is close to an actual distribution, that means that for each small box, the number of guys that land in that box is about the proportion that would be predicted by the probability distribution. So I just need to show that some number is concentrated, and I can do that with the second moment method. Yeah. And these types of anti-concentration and sub-Gaussian tails things, I mean, so at the first step, this is obvious because you have a central limit theorem saying you're approximately Gaussian. The Gaussian distribution is definitely sub-Gaussian. And anti-concentration, well, you can get that from a sufficiently quantitative central limit theorem, or or something. There's all sorts of things you can do. Now, yeah, so at each subsequent step, you have to imitate that, but using random graphs with a fixed degree sequence. And that's annoying, but you're sort of guided by what works in the GNP case, in the GN1/2 case. And yeah.
All right, thank you. And maybe one more question. So about, can you generalize this for others P? So so this stuff by Mackey and others can be applied for many settings, for many I mean range of degrees,
So,
right? So
were we saying Mikey at this one?
Mackey.
Oh, McKay. Yes, absolutely. That's a great question. So, in fact, so what we've written, I mean, it's so technical that we sort of didn't want to generalize it more than we needed to. But for this majority dynamics thing, my co-authors, they generalized it for arbitrary P. So arbitrary fixed P. P does not depend on N. They generalized the machinery, which means that now if you went and applied that to this Füredi problem, so a random graph of any density, you should get exactly the same theorem, that you find a bisection where almost all vertices are friendly. Now, of course, you can also ask for the degree to go to 0 with N. And then you no longer, I mean, then the machinery is different. You're not using this generating function, complex analysis stuff. You still know how to enumerate random graphs with a given degree sequence, but it's different methods.
Yeah.
I'm not sure whether there would be obstacles towards doing that. I mean, you would obviously just try to go and substitute everything with that machinery, but I'm not sure whether you'd run into problems. So I think that probably the theorem is true for basically any density. So for very, very sparse graphs where like the number of edges is linear and the number of vertices, I think the behavior might be a bit different, but anything above that, I think it should be very similar.
It may be even simpler to prove it for sparse settings.
But perhaps, yeah, that's quite possible. Yeah.
Okay, thanks. Any other questions? Well, it seems that there are no more questions. Yeah, but it's a little bit more that you predicted. I think it's a little bit more than 1 hour.
Yes, yeah. I tried to, yeah.
Yeah, but you're very fast. So I think that some places were difficult to understand, but the overall idea is clear. And
okay.
But yeah, I see there are many difficult technical things, and that can be understood only if we go deeper in the paper. And I have already looked on the paper; it's long.
Yeah, well, there's like 2 sections. There's the section reducing it to a concentration problem. That's short. And then there's actually proving the concentration, and you have to all this machinery with the degree distributions and studying distances and studying random regular graphs, constrained degree random graphs and stuff. So I guess that's a reason why I would be very interested if there was a softer way to do the second part of the paper. Yeah.
Okay, thank you very much. Thanks for giving the lecture. Goodbye and bye, everyone. See you next week.
Okay.